So the class today is Introduction to Natural Language Processing, and I'll be talking a little bit about, what is natural language processing, why we're motivated to do it, and also some of the difficulties that we encounter. And at the end, I'll also be talking about class logistics, so you can ask any logistics questions at that time. So if we talk about what is NLP anyway, does anyone have any opinions about the definition of what natural language processing would be? Oh, one other thing I should mention is I am recording the class. I put the class on YouTube afterwards. I will not take pictures or video of any of you, but if you talk, your voice might come in the background, so just be aware of that. Usually not, it's a directional mic, so I try to repeat the questions after everybody, but for the people who are listening to the recordings. So anyway, what is NLP anyway? Does anybody have any ideas about the definition of what NLP might be? Yes.
So it helps machines to understand human languages better. So the facilitate human and machine interaction.
Okay. So the answer was it helps machines understand language better. So to facilitate human and human machine interactions. I think that's very good. It's almost similar to what I have written on my slide here. But in addition to natural language understanding, there's one major other segment of NLP. Does anyone have an idea what that might be? We often have a dichotomy between two major segments, natural language understanding and natural language generation. Yeah, exactly. So I would say that's almost perfect if you had said understand and generate. So very good. So I say technology to handle human language, usually text using computers, to aid human-machine communication. And this can include things like question answering, dialogue, or generation of code that can be executed with computers. It can also aid human-human communication, and this can include things like machine translation or spell checking or assisted writing. And then a final segment that people might think about a little bit less is analyzing and understanding a language. And this includes things like syntactic analysis, text classification, entity recognition, and linking. And these can be used for various reasons, not necessarily for direct human-machine communication, but also for like aggregating information across large things for scientific studies and other things like that. And I'll give a few examples of this. We now use NLP many times a day, sometimes without even knowing it. So whenever you're typing a doc in Google Docs, there's spell checking and grammar checking going on behind. It's gotten frighteningly good recently, where it checks like most of my mistakes and rarely flags things that are not mistakes. So obviously they have powerful models running behind that. And it can do things like answer questions. So I asked ChatGPT, who is the current president of Carnegie Mellon University? And ChatGPT said, I did a quick search for more information. Here's what I found. The current president of Carnegie Mellon University is Farnham Jahanian. He has been serving since July 1st, et cetera, et cetera. So as far as I can tell, that's correct. At the same time, I asked how many layers are included in the GPT 3.5 Turbo architecture. And it said to me, GPT 3.5 Turbo, which is an optimized version of GPT 3.5 for faster responses, doesn't have a specific layer architecture like the traditional GPT-3 models. And I don't know if this is true or not, but I'm pretty sure it's not true. I'm pretty sure that, GPT is a model that's much like other models. So it basically just made up the spec because it didn't have any information on the internet or couldn't talk about it. So another thing is NLP can translate text pretty well. So I ran Google Translate on Japanese. This example is a little bit old. It's from a few years ago about COVID, but I retranslated it a few days ago, and it comes up pretty good. You could basically understand what's going on here. It's not perfect, but you can understand the general gist. At the same time, if I put in a relatively low resource language, this is Kurdish. it has a number of problems when you try to understand it. And just to give an example, this is talking about some paleontology discovery. It called this person a fossil scientist instead of the kind of obvious English term paleontologist. And it's talking about 3 different T-Rex species, how T-Rex should actually be split into 3 species, where T-Rex says king of ferocious lizards, Imperator says emperor of savage lizards, and then T. Regina means queen of ferocious snail. I'm pretty sure that's not snail. I'm pretty sure that's lizard. So you can see that this is not perfect either. Some people might be thinking, why Google Translate and why not GPT? Well, it turns out, according to one of the recent studies we've done, GPT is even worse at these low resource languages. So I use the best thing that's out there. Another thing is language analysis can aid scientific inquiry. So this is an example that I've been using for a long time. It's actually from Martin Sapp, another faculty member here, but I have been using it since like before he joined. And this is an example from computational social science, answering questions about society given observational data. And their question was, do movie scripts portray female or male characters with more power or agency in movie script films? So it's asking kind of a societal question by using NLP technology. And the way they did it is they basically analyzed text, trying to find the agents and patients in a particular text, which are the things that are doing things and the things that things are being done to. And you can see that essentially male characters in these movie scripts were given more power and agency, and female characters were given less power and agency. And they were able to do this because they had NLP technology that analyzed and extracted useful data and turned it into a very easy form to do kind of analysis of the variety that they want. So I think that's a major use case of NLP technology that does language analysis nowadays. Turn it into a form that allows you to very quickly do aggregate queries and other things like this. But at the same time, language analysis tools fail at very basic tasks. So these are some things that I ran through a named entity recognizer. And these were kind of very nice named entity recognizers that a lot of people were using. For example, Stanford Core NLP and Spacey. And both of them, I just threw in the first thing that I found on the New York Times at the time. And it basically made at least one mistake in the first sentence. And here it recognized Baton Rouge as an organization. And here it recognized Hurricane Ida as an organization. So like even these things that we expect should work pretty well make pretty silly mistakes. So in the class, basically what I want to cover is what goes into building state-of-the-art NLP systems that work really well on a wide variety of tasks. Where do current systems fail? And how can we make appropriate improvements and achieve whatever we want to do with NLP? And this set of questions that I'm asking here is exactly the same as the set of questions that I was asking 2 years ago before ChatGPT. I still think they're important questions, but I think the answers to these questions is very different. And because of that, we're updating the class materials to try to cover, the answers to these questions in kind of the era of large language models and other things like that. So that's all I have for the intro. Maybe pretty straightforward. Are there any questions or comments so far? If not, I'll just go on. Okay, great. So I want to first go into a very high-level overview of NLP system building. And most of the stuff that I want to do today is to set the stage for what I'm going to be talking about in more detail over the rest of the class. And we could think of NLP systems through this kind of general framework where we want to create a function to map an input X into an output Y, where X and or Y involve language. And do some people have favorite NLP tasks or NLP tasks that you want to be handling in some way? Or maybe what do you think are the most popular and important NLP tasks nowadays? Okay, so translation is maybe easy. What's the input and output of translation? Okay, yeah, so in translation, input's text in one language, output is text in another language. And then what is a good translation? When the yeah, correct, or the same is the input, basically, yes. It also should be fluent, but I agree. Any other things? Generation, the reason why I said it's tough is it's pretty broad, and it's not like we could be doing generation with lots of different inputs, but yeah, any other things, maybe a little bit different? Yeah. Maybe like a scenario and a multiple choice question? A scenario and a multiple choice question about the scenario. And so what would the scenario and the multiple choice question are probably the input, and then the output is an answer to the multiple choice question. And then there it's kind of obvious, like what is good, it's the correct answer, sure. But interestingly, I think a lot of LLM evaluation is done on these multiple choice questions, but I'm yet to encounter an actual application that cares about multiple choice question answering. So there's kind of a funny disconnect there, but yeah, I saw it down there. Think about vector search and search in general. Yeah, vector search. That's very good. So the input is textual. You can convert it into an element or just get the semantic understanding and you map it to another language domain where it's, okay, yeah, so I'd say the input there is a query and a document base. And then the output is maybe an index into the document or something else like that, sure. And then something that's good. Here's a good question. What's a good result from that? What's a good output? Similar, but the major problem there I see is how do you define similar and how do you define a good threshold such that, hey, there could always be a closest, like when you understand whether the query that's research is actually not in the table. Yeah, exactly. So that just to repeat, it's like we need to have a similarity, a good similarity metric. We need to have a good threshold where we get like the ones we want and we don't get the ones we don't want. And we're going to talk more about that in the retrieval lecture, exactly how we evaluate and stuff. But yeah, good. So this is a good, here are some good examples. I have some examples of my own. The first one is kind of the very generic one, maybe kind of like generation here, but text and continuing text. So this is language modeling. So you have a text and then you have the continuation. You want to predict the continuation. Text and text in another language is translation. Text in a label could be text classification. Text and linguistic structure or some kind of entities or something like that could be language analysis or information extraction. We could also have image and text, which is image captioning, or speech and text, which is speech recognition. And I take the very broad view of natural language processing, which is if it's any variety of language, if you're handling language in some way, it's natural language processing. It doesn't necessarily have to be text input, text output. So that's relevant for the projects that you're thinking about too at the end of this course. So the most common FAQ for this course is, does my project count? And if you're uncertain, you should ask, but usually like if it has some sort of language involved, then I'll usually say, yes, it does count. So if it's like code to code, that's not, code is not natural language. It is language, but it's not natural language. So that might be borderline. We might have to discuss about that. Cool. So next I'd like to talk about methods for creating NLP systems. And there's a lot of different ways to create NLP systems. All of these are alive and well in 2024. The first one is rule-based system creation. And so the way this works is like, let's say you want to build a text classifier. You just write the simple Python function that classifies things into sports or other. And the way it classifies it into sports or other is it checks whether baseball, soccer, football, and tennis are included in the document and classifies it into sports. If so, other if not. So has anyone written something like this, maybe not a text classifier, but you know, to identify entities or split words or something like that. Has anybody not ever written anything like this? Yeah, that's what I thought. So rule-based systems are very convenient when you don't really care about how good your system is. Or you're doing something that's really, really simple and it'll be perfect even if you do the very simple thing. And so I think it's worth talking a little bit about them, and I'll talk a little bit about that this time. The second thing, which very rapidly over the course of maybe 3 years or so has become actually maybe the dominant paradigm in NLP, is prompting and prompting a language model. And the way this works is you ask a language model, if the following sentence is about sports, reply sports, otherwise reply other. And you feed it to your favorite LM. Usually that's GPT something or other. Sometimes it's an open source model of some variety. And then it will give you the answer. And then finally, fine tuning. So you take some paired data and you do machine learning from paired data where you have something like, I love to play baseball. The stock price is going up. He got a hat trick yesterday. He is wearing tennis shoes. And you assign all of these labels to them, train a model. And you can even start out with a prompting-based model and fine-tune a language model also. So one major consideration when you're building systems like this is the data requirements for building such a system. And for rules or prompting where it's just based on intuition, really no data is needed whatsoever. You don't need a single example and you can start writing rules. Or just to give an example, the rules and prompts I wrote here, I didn't look at any examples and I just wrote them. So this is something that you could start out with. The problem is you also have no idea how well it works if you don't have any data whatsoever, right? So you might be in trouble if you think something should be working. So normally the next thing that people move to nowadays when they're building practical systems is rules or prompting based on spot checks. So that basically means that you start out with a rule-based system or a prompting-based system, and then you go in and you run it on some data that you're interested in. You just kind of qualitatively look at the data and say, oh, it's messing up here. Then you go in and fix your prompt a little bit, or you go in and fix your rules a little bit, or something like that. So this is kind of the second level of difficulty. So the third level of difficulty would be something like rules or prompting with rigorous evaluation. And so here you would create a development set with inputs and outputs. So you create maybe 200 to 2,000 examples and then evaluate your actual accuracy. So you need an evaluation metric, you need other things like this. This is the next level of difficulty, but if you're going to be a serious, NLP engineer or something like this, you definitely will be doing this a lot, I feel. And then so that here now you start needing a dev set and a test set. And then finally, fine tuning, you need an additional training set. This will generally be a lot bigger than 200 to 3,000 examples. And generally the rule is that every time you double your training set size, you get about a constant improvement. So if you start out down here with 0-shot accuracy with a language model, you create a small training set and you get, a pretty big increase. And then every time you double it, it increases by a constant factor. It's kind of like just in general in machine learning, this is a trend that we tend to see. So, so based on this, there's kind of you get a big gain from having a little bit of training data, but the gains very quickly drop off and you start spending a lot of time annotating data. So yeah, this is the general overview of the different types of system building. Any questions about this or comments or things like this? I think one thing that's changed really drastically from the last time I taught this class is the fact that number one and number two are the things that people are actually doing in practice, which was, people who actually care about systems are doing number one and number two is the main thing. It used to be that if you were actually serious about building a system, you really needed to do the fine tuning, and now it's kind of like more optional. So. Yeah. Yeah. Mm-hmm. So it's definitely an empirical observation. In terms of the theoretical background, I can't immediately point to a particular paper that does that, but I think if you think about I think I have seen that they do exist in the past, but I can't think of it right now. I can try to come up with an example of that. So yeah, I should take notes. Or if someone wants to share one on Piazza, if you have any ideas and want to share on Piazza, I'm sure that would be great. It'd be great to have a discussion on Piazza. Performance increase. Cool. Okay. So next, I want to try to make a rule-based system. And I'm going to make a rule-based system for sentiment analysis. And this is a bad idea. I would not encourage you to ever do this in real life, but I want to do it here to show you why it's a bad idea and like what are some of the hard problems that you encounter when trying to create a system based on rules. And then we'll move into building a machine learning based system after we finish this. So if we look at the example task, this is review sentiment analysis. It's one of the most valuable tasks that people do in NLP nowadays because it allows people to know how customers are thinking about products, improve their, their product development and other things like that, monitor people's, satisfaction with their social media service, other things like this. So basically the way it works is you have outputs, or you have sentences, inputs, like I hate this movie, I love this movie, I saw this movie, and this gets mapped into positive, neutral, or negative. So I hate this movie would be negative, I love this movie positive, and I saw this movie is neutral. So that's the task, input, text, output, labels, ternary sentence label. And in order to do this, we would like to build a model. And we're going to build the model in a rule-based way, but we'll still call it a model. And the way it works is we do feature extraction. So we extract the salient features for making the decision about what to output next. We do score calculation, calculate a score for one or more possibilities. And we have a decision function. So we choose one of those several possibilities. And so for feature extraction, formally what this looks like is we have some function and it extracts a feature vector. For score calculation, we calculate the scores based on either a binary classification, where we have a weight vector and we take the dot product with our feature vector, or we have multi-class classification where we have a weight matrix and we take the product with the vector, and that gives us, scores over multiple classes. And then we have a decision rule. So this decision rule tells us what the output is going to be. Does anyone know what a typical decision rule is? It's maybe so obvious that you don't think about it often, but a threshold. So like would that be for binary, a single binary scalar score or a multiple class? Binary, yeah. So, and then you would pick a threshold, and if it's over the threshold, you say yes, and if it's under the threshold, you say no. Another option would be you have a threshold and you say yes, no, abstain. So you don't give an answer. And depending on how you're evaluated, what is a good classifier, you might want to abstain some of the time also. For multi-class, what's a standard decision rule for multi-class? Argmax, yeah, exactly. So basically you find the index that has the highest score and you output it. We're going to be talking about other decision rules also, like self-consistency and minimum base risk later for text generation. So you can just keep that in mind, and then we'll forget about it for like several classes. So for sentiment classification, I have a code walk here. And this is pretty simple, but if you're bored of the class and would like to try out yourself, you can challenge and try to get a better score than I do over the next few minutes. But we have this rule-based classifier in here. And I will open it up in my VS Code to try to create a rule-based classifier. And basically the way this works is that we have feature extraction. We have feature extraction, we have scoring, and we have a decision rule. So here for our feature extraction, I have created a list of good words and a list of bad words. And what we do is we just count the number of good words that appeared and count the number of bad words that appeared. Then we also have a bias feature. So the bias feature is a feature that's always one. And so what that results in is we have a dimension 3 feature vector, where this is like the number of good words, this is the number of bad words, and then we have the bias. And then I also define the feature weights. So for every good word, we add 1 to our score. For every bad word, we subtract 1 from our score, and for the bias, we have 0. And so we then take the dot product between these two, and we get minus 0.5, and that gives us the score. So let's run that. And I read in some data. And what this data looks like is basically we have a review, which says The Rock is destined to be the 21st century's new Conan, and that he's going to make a splash even greater than Arnold Schwarzenegger, Jean-Claude Van Damme, or Steven Seagal. So this seems pretty positive, right? That's a pretty high order to be better than Arnold Schwarzenegger or Jean-Claude Van Damme, if you're familiar with action movies. And so, of course, this gets a positive label. And so we have run classifier. Actually, maybe I should call this decision rule, because this is essentially our decision rule. And here, I basically do the thing that I mentioned here, the yes, no, abstain, or in this case, positive, negative, neutral. So if the score is greater than 0, we return 1. If the score is less than 0, we return -1, which is negative. And otherwise, we return 0. We have an accuracy calculation function, just calculating the outputs are good. And this is the overall label count in the output. So you can see there's slightly more positives than there are negatives. And then we can run this, and we get a score of 43. And so one thing that I have found is I do a lot of kind of research on how to make NLP systems better. And one of the things I found really invaluable is if you're in a situation where you have a set task and you just want to make the system better on the set task, doing comprehensive error analysis and understanding where your system is failing is one of the best ways to do that. And I would like to do a very rudimentary version of this here. And what I'm doing essentially is I'm just randomly picking several examples that were correct. And so let's look at the examples here. Here, the true label is 0, and this predicted 1. It may not be as cutting, as witty, or as true as back in the glory days of Weekend and 2 or 3 things that I know about her. But who else engaged in filmmaking today is so cognizant of the cultural and moral issues involved in the process? So what words in here are a good indication that this is a neutral sentence? Any ideas? A little bit tough, huh? We're starting to think maybe we should be using machine learning. Even by the intentionally low standards of frat boy humor, sonority boys is a Bowser. I think frat boy is maybe negative sentiment if you're familiar with US. US. I don't have any negative sentiment, but the people who say it that way have negative sentiment, maybe. So if we wanted to go in and do that, we could maybe. I won't save this, but oh, whoops. I'll go back and fix it. Crass. Crass is pretty obviously negative, right? So I can add crass. Actually, let me just add crass. And then I'll go back and have our train accuracy. Wait, maybe I need to run the whole thing again. And that budged the train accuracy a little, the dev test accuracy, not very much. So I could go through and do this. Let me add unengaging. So I could go through and do this all day and you'd probably be very bored. Unengaging. But I won't do that because we have much more important things to be doing. So anyway, we could go through and design all of the features here. But like, why is this complicated? Like the reason why it was complicated became pretty clear from the very beginning, the very first example I showed you, which was that was a really complicated sentence. Like all of us could see that it wasn't like really strongly positive. It wasn't really strongly negative. It was kind of like in the middle, but it was in the middle and it said it in a very long way, not using any clearly positive sentiment words, not using any clearly negative sentiment words. So yeah, basically I improved. But what are the difficult cases that we saw here? So the first one is low frequency words. So here's an example. The action switches between past and present, but the material link is too tenuous to anchor the emotional connections that purport to span a 125-year divide. So this is negative. Tenuous is kind of a negative word. Purport is kind of a negative word, but it doesn't appear very frequently. So I would need to spend all my time looking for these words and trying to add them in. Here's yet another horse franchise mucking up its storyline with glitches. Casual fans could correct in their sleep. Negative again. So the solutions here are keep working until we get all of them, which is maybe not super fun. Or incorporate external resources such as sentiment dictionaries that people created. We could do that, but that's a lot of engineering effort to make something work. Another one is conjugation. So we saw unengaging, I guess. That's an example of conjugation. Some other ones are operatic sprawling picture that's entertainingly acted, magnificently shot, and gripping enough to sustain most of its 170-minute length. So here we have magnificently. So even if I added magnificent, this wouldn't have been caught, right? It's basically an overlong episode of Tales from the Crypt. So that's maybe another example. So some things that we could do, or what we would have done before the modern paradigm of machine learning, is we would run some sort of normalizer, like a stemmer or other things like this, in order to convert this into the root words that we already have seen somewhere in our data or have already handled. So that requires conjugation analysis or morphological analysis, as we say it in technical terms. Negation. This is a tricky one. So this one's not nearly as dreadful as expected. So dreadful is a pretty bad word, right? But not nearly as dreadful as expected is like a solidly neutral, you know, or maybe even positive. I would say that's neutral, but you know, neutral or positive. It's definitely not negative. Serving Sarah doesn't serve up a whole lot of laughs. So laughs is obviously positive, but not serving up laughs is obviously negative. So if negation modifies the word disregard it, now we would probably need to do some sort of syntactic analysis or semantic analysis of some variety. Metaphor and analogy. So puts a human face on a land most Westerners are unfamiliar with. This is positive. Green might want to hang on to that ski mask, as robbery may be the only way to pay for this next project. So this is saying that the movie was so bad that the director will have to rob people in order to get money for the next project. So that's kind of bad, I guess. Has all the depth of a wading pool. This is kind of my favorite one because it's really short and sweet, but you know, you need to know how deep a wading pool is. So that's negative. So the solution here, I don't really even know how to handle this with a rule-based system. I have no idea how we would possibly do this. Yet machine learning-based models seem to be pretty adept at this. Okay, and then I start doing these ones. Anyone have a good idea? Any other friends who know Japanese? No? Okay. So yeah, that's positive. That one's negative. And the solution here is learn Japanese, I guess. Or whatever other language you want to process. So like obviously rule-based systems don't scale very well. So we've moved, but like rule-based systems don't scale very well. We're not going to be using them for most of the things we do in this class. But I do think it's sometimes useful to try to create one for your task, maybe right at the very beginning of a project, because it gives you an idea about what's really hard about the task in some cases. So yeah, I wouldn't entirely discount them. I'm not introducing them for no reason whatsoever. So next is machine learning based NLP. And machine learning in general, here actually, when I say machine learning, I'm going to be talking about the traditional fine-tuning approach where we have a training set, dev set, test set. And so we take our training set, we run some learning algorithm over it. We have a learned feature extractor F, possibly learned feature extractor F, possibly learned scoring function W. And then we apply our inference algorithm, our decision rule, and make decisions. When I say possibly learned, actually the first example I'm going to give of a machine learning based technique is doesn't have a learned feature extractor, but most things that we use nowadays do have learned feature extractors. So our first attempt is going to be a bag of words model. And the way a bag of words model works is essentially we start out by looking up a vector where one element in the vector is 1 and all of the other elements in the vector are 0. And so if the word is different, the position in the vector that's 1 will be different. We add all of these together, and this gives us a vector where each element is the frequency of that word in the vector. And then we multiply that by weights, and we get a score. And here, as I said, this is not a learned feature vector. This is basically, sorry, not a learned feature extractor. This is basically a fixed feature extractor, but the weights themselves are learned. So my question is, I mentioned a whole lot of problems before. I mentioned infrequent words. I mentioned conjugation. I mentioned different languages. I mentioned syntax and metaphor. So which of these do we think would be fixed by this sort of learning-based approach? Any ideas? Maybe not fixed, maybe made significantly better. Any brave people? Maybe negation? Okay, so maybe doesn't would have a negative vote, yeah.
conjugation is like the conjugation of them.
Yeah, so for the conjugation, if we had the conjugations of the stems mapped to the same position, that might fix the conjugation problem. But I would say if you don't do that, then this kind of fixes conjugation a little bit, but maybe not really. Yeah.
Kind of fix conjugation because like if they're using different types of the same word, there's probably likelihood that in our train set we'll see different variations. So we'll learn how to classify a sentence with the surrounding structure than the word frame.
Yeah, if it's a big enough training set, you might have covered the various conjugations, but if you haven't and you don't have any rule-based processing, it might still be problems. Yeah. Yeah, so infrequent words, if you have a large enough training set, yeah, you'll be able to fix it to some extent. So none of the problems are entirely fixed, but a lot of them are made better. Different languages is also made better if you have training data in that language, but if you don't, then you're out of luck. So now what I'd like to do is I'd like to look at what our vectors represent. So basically, in binary classification, each word, so the vectors themselves represent the counts of the words. Here I'm talking about what the weight vectors or matrices correspond to. And the weight vector here will be positive if the word it tends to be positive if in a binary classification case. In a multi-class classification case, we'll actually have a matrix that looks like this, where each column or row corresponds to the word, and each row or column corresponds to a label. And it will be higher if that row tends to correlate with that. That word tends to correlate with that label. So this training of the bag of words model can be done so simply that we can put it in a single slide. So basically here, what we do is we start out with the feature weights. And for each example in our data set, we extract features. The exact way I'm extracting features is basically splitting the words using the Python split function and then counting the number of times each word exists. We then run the classifier. So actually running the classifier is exactly the same as what we did for the rule-based system. It's just that we have feature vectors instead. And then if the predicted value is not equal value, then for each of the features in the feature space, we upweight the weight by the vector size, by the amount of the vector if y is positive, and we downweight the vector by the size of the vector if y is negative. So this is really, really simple. It's probably the simplest possible algorithm for training one of these models. But I have an example in this that you can also take a look at. Here's the trained bag of words classifier. And we can step through. This is on exactly the same data set as I did before. We're training on the training set and evaluating on the dev set. I also have some extra stuff, like I'm shuffling the order of the data IDs, which is really important if you're doing this sort of incremental algorithm, because what if your training data set was ordered in this way, where you have all of the positive labels on top, and then you have all of the negative labels on the bottom? If you do something like this, it would see only negative labels at the end of training, and you might have problems because your model would only predict negatives. So we also shuffle data and then step through. We run the classifier. And I'm going to run 5 epochs of training through the data set very fast and calculate our accuracy. And this got 75% accuracy on the training data set and 56% accuracy on the dev data set. So if you remember, our rule-based classifier had 42 accuracy, and now our training-based classifier has 56 accuracy, but it's overfitting heavily to the training set. So basically, this is a pretty strong advertisement for why we should be using machine learning. You know, the amount of code that we had for this machine learning model is basically very similar. It's not using any external libraries, but we're getting better at this. Cool. So, cool. Any questions here? And so I'm going to talk about the connection between this algorithm and neural networks in the next class, because this actually is using a very similar training algorithm to what we use in neural networks with some particular assumptions. Cool. So what's missing in bag of words? Still, handling of conjugation or compound words is not perfect. We can do it to some extent to the point where we can memorize things. So I love this movie. I love this movie. Another thing is handling word similarities. So I love this movie and I adore this movie. These basically mean the same thing. As humans, we know they mean the same thing. So we should be able to take advantage of that fact to learn better models, but we're not doing that in this model at the moment because each unit is treated as a atomic unit and there's no idea of similarity. Also, handling of combination features. So I love this movie and I don't love this movie. I hate this movie and I don't hate this movie. Actually, this is a little bit tricky because negative words are slightly indicative of it being negative, but actually what they do is they negate the other things that you're saying in the sentence. So, like, love is positive, hate is negative, but like, don't love it's actually kind of like this, right? Like, love is very positive, hate is very negative, but don't love is like slightly less positive than don't hate, right? So it's actually kind of tricky because you need to combine them together and figure out what's going on based on that. Another example that a lot of people might not think of immediately, but is super, super common in sentiment analysis or any other thing, is but. So basically what but does is it throws away all the stuff that you said before, and you can just pay attention to the stuff that you saw beforehand. So like we could even add this to our, like if you want to add this to your role-based classifier, you can do that. You just search for but and delete everything before it and see if that improves your accuracy. Might be a fun, very quick thing to do. Cool. So the better solution, which is what we're going to talk about for every other class other than this one, is neural network models. And basically what they do is they do a lookup of dense word embeddings. So instead of looking up individual sparse vectors, individual one-hot vectors, they look up dense word embeddings and then throw them into some complicated function to extract features. And based on the features, multiply by weights and get a score. And if you're doing text classification in the traditional way, this is normally what you do. If you're doing text classification with something like prompting, you're still actually doing this because you're calculating the score of the next word to predict. And that's done in exactly the same way. So even if you're using a large language model like GPT, this is still probably happening under the hood unless OpenAI invented something that very different and alien than anything else that we know of. But I'm guessing that that probably hasn't happened. One nice thing about neural networks is neural networks theoretically are powerful enough to solve any task if you make them deep enough or wide enough. Like if you make them wide enough and then if you make them deep, it also helps further. So anytime somebody says, well, you can't just solve that problem with neural networks, you know that they're lying, basically, because they theoretically can solve every problem. But you have issues of data, you have issues of other things like that. So, you know, they don't just necessarily work out of the box. Cool. So the final thing I'd like to talk about is the roadmap going forward, some of the things I'm going to cover in the class, and some of the logistics issues. So the first thing I'm going to talk about in the class is language modeling fundamentals. And so this could include language models that just predict the next words. It could include language models that predict the output given the input or the prompt. I'm going to be talking about representing words how we get word representation, subword models, other things like that. Then go kind of deeper into language modeling. How do we do it? How do we evaluate it? Other things. Sequence encoding. And this is going to cover things like transformers, self-attention models, but also very quickly CNNs and RNNs, which are useful in some cases. And then we're going to specifically go very deep into the transformer architecture and also talk a little bit about some of the modern improvements to the transformer architecture. So the transformer we're using nowadays is very different than the transformer that was invented in 2017. So we're going to talk, well, I wouldn't say very different, but different enough that it's important. So we're going to talk about some of those things. Second thing I'd like to talk about is training and inference methods. So this includes generation algorithms. So we're going to have a whole class on how we generate text in different ways. Prompting, how we can prompt things. I hear world-class prompt engineers make a lot of money nowadays, so you'll want to pay attention to that one. And instruction tuning. So how do we train models to handle a lot of different tasks? And reinforcement learning. So how do we, like actually generate outputs, kind of judge them and then learn from that. Also experimental design and evaluation. So experimental design, so how do we design an experiment well, so that it backs up what we want to be, our conclusions that we want to be backing up? How do we do human annotation of data in a reliable way? This is getting harder and harder as models get better and better because getting humans who don't care very much about the annotation task, they might do worse than GPT-4s. So you need to be careful of that. Also debugging and interpretation techniques. So what are some of the automatic techniques that you can do to quickly figure out what's going wrong with your models and improve them? And bias and fairness considerations. So it's really, really important nowadays that models are being deployed to real people in the real world and like actually causing harm to people in some cases, that we need to be worried about that. Advanced training and architectures. So we're going to talk about distillation and quantization. How can we make small language models that actually still work well, like not large? You can run them on your phone, you can run them on your local laptop. Ensembling and mixtures of experts. How can we combine together multiple models in order to create models that are better than the sum of their parts? And retrieval and retrieval augmented generation. Long sequence models. So how do we handle long outputs? We're going to talk about applications to complex reasoning tasks, code generation, language agents, and knowledge-based QA and information extraction. I picked these because they seem to be maybe the most important, at least in research nowadays. And also they cover the things that when I talk to people in industry are kind of most interested in. So hopefully it'll be useful regardless of whether you plan on doing research or plan on doing industry related things. By the way, the two things that when I talk to people in industry, they're most interested in are RAG and code generation at the moment for now. So those are ones that you'll want to pay attention to. And then finally, we have a few lectures on linguistics and multilinguality. I love linguistics, but to be honest, at the moment, most of our cutting edge models don't explicitly use linguistic structure. But I still think it's useful to know about it, especially if you're working on multilingual things, especially if you're interested in very robust generalization to new models. So we're going to talk a little bit about that. And also multilingual NLP. I'm going to have one lecture. So also, if you have any suggestions, we have 2 guest lecture slots still open that I'm trying to fill. So if you have any things that you really want to hear about, I could either add them to the existing, content, or I could invite a guest lecturer who's working on that topic. So, please feel free to tell me. Then the class format and structure, the class content. My goal is to learn in detail about building NLP systems from a research perspective. So this is a 700 level course. So it's aiming to be for people who really want to try new and innovative things in kind of natural language processing. it's not going to focus solely on re-implementing things that have been done before, including in the project. I'm going to be expecting everybody to do something that's kind of new, whether it's coming up with a new method or applying existing methods to a place where they haven't been used before, or building out things for a new language or something like that. So that's kind of one of the major goals of this class. Learn basic and advanced topics in machine learning approaches to NLP and language models. Learn some basic linguistic knowledge useful in NLP. See case studies of NLP applications, and learn how to identify unique problems for each. One thing I'd like to point out is I'm not going to cover every NLP application ever, because that would be absolutely impossible. NLP is being used in so many different areas nowadays. But what I want people to pay attention to, like, even if you're not super interested in code generation, for example, what you can do is you can look at code generation, look at how people identify problems, look at the methods that people have proposed to solve those unique problems, and then kind of map that, try to do some generalization onto your own problems of interest. So that's kind of the goal of the NLP applications. Finally, learning how to debug when and where NLP systems fail and build improvements based on this. So ever since I was a graduate student, this has been like one of the really important things that I feel like I've done well or done better than some other people. And I feel like it's a really good way to, like, even if you're only interested in improving accuracy, knowing why your system's failing still is the best way to do that, I feel. So I'm going to put a lot of emphasis on that. In terms of the class format, before class, for some classes, there are recommended reading. This can be helpful to read. I'm never going to expect you to definitely have read it before the class, but I would suggest that maybe you'll get more out of the class if you do that. During class, we'll have the lecture and discussion with everybody. Sometimes we'll have a code or data walk. Actually, this is a little bit old. I have this slide. This year, we're going to be adding more code and data walks during office hours. And the way it will work is one of the TAs, we have 7 TAs who I'm going to introduce very soon, but one of the TAs will be doing this kind of recitation where we go over a library. So if you're not familiar with the library and you want to be more familiar with the library, you can join this, and then we'll be able to do this. And this will cover things like PyTorch and sentence piece. We're going to start out with Hugging Face, inference stuff like VLLM, debugging software like Xeno. What were the other ones? Oh, the OpenAI API and Light LLM, other stuff like that. So we have lots of them planned. We'll update that. And then after class, after almost every class, we'll have a quiz. And the quiz is intended to just, make sure that you paid attention to the material and are able to answer questions about it. We will aim to release it on the day of the course, the day of the actual lecture, and it will be due at the end of the following day of the lecture. So it will be 3 questions. It probably shouldn't take a whole lot of time, but yeah, so we'll have that. In terms of assignments, assignment 1 is going to be build your own llama. And so what this is going to look like is we're going to give you a partial implementation of Llama, which is kind of the most popular open source language model nowadays, and ask you to fill in the parts. We're going to train a very small version of Llama on a small data set and get it to work. And the reason why it's very small is because the smallest actual version of Llama is 7 billion parameters. And that might be a little bit difficult to train with resources. For assignment 2, we're going to try to do an NLP task from scratch. And so the way this will work is we're going to give you an assignment, which we're not going to give you an actual data set. And instead, we're going to ask you to perform data creation, modeling, and evaluation for a specified task. And so we're going to tell you what to do, but we're not going to tell you exactly how to do it. But we're going to try to give as concrete directions as we can. Yeah. Will you be given a parameter limit on the model? So that's a good question, or like a expense limit or something like that. I should take a break from the assignments and talk about compute. So right now, for assignment 1, We're planning on having this be able to be done either on a Mac laptop with an M1 or M2 processor, which I think a lot of people have, or Google Colab. So it should be like sufficient to use free computational resources that you have. For number two, we'll think about that. I think that's important. We do have Google Cloud credits for $50 for everybody, and I'm working to get AWS credits for more. But the cloud providers nowadays are being very stingy. So it's been a little bit of a fight to get credits, but it is very important. So I'm going to try to get as many as we can. And so, yeah, I think basically there will be some sort of like limit on the amount of things you can practically do. And so because of that, I'm hoping that people will rely very heavily on pre-trained models, pre-trained models. And yeah, so that's the short story there. The second thing, the assignment 3 is to do a survey of some sort of state-of-the-art research and do a re-implementation of this. And in doing this, again, you will have to think about something that's feasible within computational constraints. And so you can discuss with your TAs about the best way to do this. And then the final project is to perform a unique project that either improves on the state of the art with respect to whatever you would like to improve with. This could be accuracy for sure. This could be efficiency. It could be some sense of interpretability, but if it's going to be something like interpretability, you'll have to discuss with us what that means, like how we measure that, how we can like actually say that you did a good job of improving that. Another thing that you can do is take whatever you implemented for assignment 3 and apply it to a new task or apply it to a new language that has never been examined before. So these are also acceptable final projects. But basically the idea is for the final project, you need to do something new that hasn't been done before and create new knowledge with respect to NLP. So for this, the instructor is me. I'm looking forward to, discussing and working with all of you. For TAs, we have 7 TAs. 2 of them are in transit, so they're not here today. The other ones, TAs, would you mind coming up to introduce yourself? So, yeah, Nihir and Akshay couldn't be here today because they're traveling. I'll introduce them later because they're coming next time. Cool. And what I'd like everybody to do is say, like, what your name is, what your, like, maybe what you're interested in. And the goal of this is number 1, for everybody to know who you are, and number 2, for everybody to know who the best person to talk to is if they're interested in particular things. So.
Hi, I'm Akila Yadpal, in second year PhD student of marketing. I work on language generation, social bias, and common sense reasoning.
I'm Vijay Viswanathan. I'm a second-ish year PhD student led by Graham and CMU. My research is like started on the border of NLP and human-computer interaction. It's a lot of work on automating parts of the developer experience to make it easier for anyone to build or modify an NLP system.
I'm Vishwa. I'm a postdoc student. I'm working with a person after integrating hallucination with data and something.
Hi everyone, I'm Nishan. I'm a first year PhD student working on beyond and working with integrability, memory, and control. I don't like updating parameters of models, so I hope to not update parameters of models in my research. I'm a fifth year PhD student working with my primary interests are in information extraction and technical.
Yeah, thanks a lot, everyone. And yeah, thank you. And so we will we'll have people kind of have office hours. Every TA has office hours at a regular time during the week. Please feel free to come to their office hours or my office hours. I think they Vishwa, are they posted on the site? Or okay, yeah, they either are or will be posted on the site very soon. and come by to talk about anything. If there's nobody in my office hours, I'm happy to talk about things that are unrelated, but if there's lots of people waiting outside the door, I might limit it to, just things about the class, so. Cool, and we have Piazza, we'll be checking that regularly, striving to get you an answer in 24 hours on weekdays. Over weekends, we might not, so, yeah. So that's all, for today. Are there any questions?